So I did my paper over I chose the paper real-time self-adjusting LQR method for autonomous vehicle lateral control. Um, so first, we're going to address the application and scope of the paper. Autonomous cars greatly improve safety by reducing the risks of accidents caused by driving errors. A big factor in this, lateral and longitudinal control. Um, it plays a crucial role in achieving successful autonomous driving. Lateral control is important for maneuvers such as lane changes, obstacle avoidance, and turning at intersections, making precise lateral tracking control essential for driving safety and reliability. Um, this paper goes into detail about the shift to LQR controllers and the limitations of other LQR algorithms used in other studies. The biggest limitation that other studies suffer from is that they neglect the calculation errors caused by the decrease in lateral stiffness. Lateral stiffness refers to a tire's resistance to lateral deflection when a side force is applied, which influences cornering, handling characteristics, and tracking error of the control system. The paper goes with a real-time parameter self calibrating LQR method, and that's proposed to account for the tracking error that's present in the other studies. The three main identifying characteristics of this method are the regression model based on a shallow neural network, which is introduced to estimate the lateral stiffness of each tire in real time. The second, the vehicle dynamics model and a vehicle road error model, which are established to model the lateral trajectory tracking system as a time varying linear system. And then the last characteristic of this method is a feed forward and feedback optimal controller, which utilizes the estimated lateral stiffness to achieve real-time self-calibration of some parameters. Uh, um, this study shows that through their simulation that the proposed RTA LQI algorithm can significantly improve lateral tracking, demonstrating excellent accuracy, stability, and robustness for emergency avoidance and long distance cruise conditions. So next, we're going to talk about some of the mathematical models used throughout the paper. The first one that I'm going to show is the block diagram of the RTA LQR uh, controller. Look at the block diagram. We can see how the reference trajectory is used for the basis of the time varying linear system. This then feeds into the neural network and is then interpolated. The output of the interpolation is then fed into the RTA controller. Next, we're going to talk about the vehicle road error model. Uh, here we can see here we can see that the model is used to describe the trajectory tracking error, where capital XY uh, is the coordinate system and lowercase xy is the vehicle coordinate system. The vertical line D is drawn from the origin of the vehicle coordinate system to the reference track. The point where line D meets the reference track is the projection point. The angle theta between the vehicle speed direction and the capital x-axis is called the vehicle heading angle. The tangent positive direction of the track at the projection point and the capital X-axis is the reference heading or theta r. Then last model we're going to talk about that they use in the paper is the dynamic space vehicle road error model. Here we can see that XE is the state vector, U is the input, and W is for the disturbance. And then below that, we can see the real-time updating matrices, AET, BET, and DET. Next, we're going to talk about the cost function and the optimization technique used in the paper. So here we can see the cost function and the weights Q and R. And the goal of this cost function is to minimize the lateral and heading tracking errors as much as possible. So essentially, the control objective is to keep the state vector xe equal to 0. After that, we're going to consider some of the pros and cons discussed in the paper. One of the main advantages of the LQR system described in the paper is the increase in control accuracy compared to other systems proposed by scholars. The RTAA LQR algorithm reduces the maximum absolute transverse error by 46.6% compared to the improved LQR controller, which is a pretty drastic reduction in error. Next, we're going to talk about a con, which is the approach to varying transverse and longitudinal acceleration when a car travels along a curve. This impacts the accuracy of the transverse controller. The RTA LQR controller demonstrated improved robustness and tracking accuracy over the LQR controller, the tracking of curved roads. However, road curvature just adds another degree of uncertainty to the control system, which impacts the reliability of the data and the accuracy of the simulations that they include within the study. And then lastly, we're going to discuss any assumptions used within the paper. So one of the main assumptions used in the paper is the estimation of tire lateral stiffness. Um, this is because time varying lateral stiffness of tires cannot be directly measured. So the lateral stiffness is estimated by obtaining the tire slip angle and vertical tire forces, and then they use interpolation to fit the lateral stiffness. The neural network is the proposed solution for this issue, since neural networks have strong fitting capabilities for nonlinear and unknown relationships. So the neural network may increase accuracy, but it's still dependent on estimation and the unknowns and probable error that comes with this estimation. And here is the citation of the paper.